Hi, so what we're talking about today might leave you a little salty: electrolytes and colligative properties. So we're going to start not with a salt, but with a sugar. As you see, as we go to the right, a little bit of sugar, a lot, a medium amount, a lot, we're increasing our concentration. The other way is increasing our dilution. So if your solution is unsaturated, then it is on the dilution side. If your solution is on the supersaturated side, then it is on the concentrated side. And that's all how the solute, in this case sugar, compares to the solvent, which is typically water, to make those solutions. All right, so here we have sugar. Glucose is C6H12O6. Sucrose is C12H22O11. For our sake today, they are going to work similarly. As you increase the temperature, so as we go to the right on the graph, their solubility increases. The amount of sugar that can be dissolved in water increases as we increase the temperature. Hot tea, you can get more sugar dissolved than cold tea. That's all that is saying here. Okay. Sugar is a polar covalent molecule. It does dissolve in water, again, because we can see on the graph, we can look between 0 and 100 degrees, and there is at least some sugar, either 180 or up here at 300 in our graph. And in fact, this graph is just going to keep going, so it's even higher. When it's in solution, we can also call that an aqueous sugar solution. Aqueous just means dissolved in water. So quick double check that these graphs are making sense. What temperature do you need to dissolve 220 grams in 100 grams of water? So if we look over here, look, this graph is all about the 100 grams of water. So we don't need to use that in our analysis. We do have to plot where the 220 is. So here's 220 for the solubility. And I'm going to just draw that line all over here. And we see that little intersection point of the solubility graph with the 220. If it is on the line, that is saturated. So we're looking for the saturated conditions, 220 grams of sugar per 100 grams of water, and what temperature that happens at. So we need to find the x-axis number. I'm going to bring a line down here. It's just slightly over half. So probably anything between 30 to 35, if you were to type it in, would give you credit unless they want a really exact number, in which case you use your ruler as a scale. Okay. So you might have heard this before: like dissolves like. Polar substances dissolve both ionic and polar because they both have those poles of plus and minus. Okay, it's just either a dipole moment or a true ion plus and minus. The universal solvent is water. It's accessible, it's in lots of places, and it's polar, so it fits there. Water can dissolve both ionic and polar substances. Nonpolar substances dissolve nonpolar substances. So nonpolar substances, one example would be benzene, which is C6H6. So if I put benzene with a nonpolar substance, it tends to dissolve, which means it's a physical change and goes into solution. How can you remember which one's which? This is a polar bear in water. Polar bear is using the water as the universal solvent. Okay. Now, how do we know if we can be dissolved in water like our polar bear here, or if we cannot be dissolved in water? First step, decide if it's ionic or covalent. Remember, ionic has ions, covalent has all nonmetals. And if you just see the name, you're going to see some prefixes. That's not true 100% of the time, but it will get you there most of the way. Okay. If it's ionic, you know right away that the polar substance needs to be used as a solvent. If it's covalent, you need to draw to determine if it's polar or non-polar. So draw those Lewis dot structures. So magnesium chloride, magnesium has a +2 charge. Chlorine has a -1, a cation and an anion. So even if you don't remember that you have to crisscross to get those charges there, for the chemical formula, you still see that they are ions. So this is ionic. So they will dissolve in water. So as long as the chemical is soluble in water, it will dissolve in water. There are some ionics that are strong enough that they will not dissolve in water. Okay, but the general rule of thumb, like dissolves like, ionics can be dissolved by water. CH2O, carbon in the center, hydrogen on the outside, oxygen somewhere. Oxygen wants 2 bonds, hydrogen always wants 1 bond. Double check. I got 4 valence electrons of carbon. Carbon is showing his complete octet of 8. Hydrogen only gets 2 for their octet. This oxygen over here, he needs 1, 2, 3, 4. This is what our structure looks like. What are rules for polarity? First, you look for lone pairs on the central atom. So on the center here, we do not have lone pairs. Remember, the lone pairs are the unbonded electrons. So those are the dots, not the bars. So everything in carbon right now has a bar, so there are no lone pairs. If you see 1 to 2 lone pairs, it is typically going to be polar. The other rule for polarity is symmetry. When I look here, I have different outer atoms, okay? Which means I have an unequal distribution of electrons. So we don't have the lone pairs giving it polarity, but we do have the asymmetricness. So we have asymmetry there. Asymmetry is going to give us polar because we are unequal. So CH2O is polar, so it will dissolve in water. Carbon dioxide, carbon in the center, oxygen on the outside. Oxygen likes double bonds. And he wants to have 8 valence electrons in the octet. This is carbon dioxide. So when we look at him, we have no lone pairs. And we have symmetry. No lone pairs in symmetry is nonpolar because we have equal distribution of electrons. So no lone pairs, and it's symmetric, it's nonpolar. 1 to 2 lone pairs or asymmetry, and it is polar. So in this case, CH2O, we're polar because of asymmetry, but we could also be polar because of lone pairs on other options. Sulfuric acid, sulfuric, ic equals 8, so that's sulfate, and acid tells us that we're crisscrossed with the hydrogen. So we are going to have H2SO4 is sulfuric acid, cation and anion. So even though these are all nonmetals, we do have a strong charge and ability to change into ions. So this guy does dissolve in water. Okay. Okay, and so for that, acids are always aqueous. So anytime you see an acid there, the reason why it gets that acid status is because it's pulling those H pluses out as ions. So it is going to dissolve in water. So 1, 2, and 4 dissolve in water here. Acids are aqueous. CH2O has different outer atoms, making asymmetrical, and magnesium chloride is ionic. Those all will dissolve in water because water is polar. So here we got pictures here. You can see these ones here are water. You can picture that Mickey Mouse, these little H's ears, and the nose is that O for oxygen. Those guys are polar. You just can't see it here because they have the lone pairs as well. Water is polar. And so he's going to start to pick apart this potassium chloride. It's going to go in and become pushy, and push himself in between all of these ions to spread them out. Okay, this is called dissociation. Ions. Dissociation is spreading them out into their ions. It's a physical change. They're just pushing their way in between the bond, but these are still positive and negative, so they are still drawn to each other like opposites attract. Okay. If you are an ionic that's soluble in water or a strong acid, you dissociate 100%, regardless of your molarity. Okay, you're going to spread out kind of to fit the space of the container. Those water molecules are going to be attracted to your different charges and push in there. Weak acids don't spread out 100%. So you'll see some spread apart and some will stay in their little clumps. Okay, but if I dilute, if I give them some more water, and there's more water to be pushy. So those weak acids don't split apart 100%, but if I add some more water, I have more water being pushy, and that does increase them splitting into their ion states. Now, what are these things called that split into their ion states? Electrolytes, electricity. That's the main thing to remember. If we have ions, we can get a chain of ions coming, and that is how electricity is going to work. It's going to jump back and forth from what we are creating. You need to have those differences in charges. Okay, if it disassociates 100%, that means you got a lot of ions to deal with, so it's strong. If it doesn't disassociate 100%, then it's weak. If it doesn't split into ions, then it's a non-electrolyte. So lots of key terms there. Let's see how this goes. Here's a nice little picture to look at for the electricity. Strong electrolyte. Okay, so here we have an ionic. Strong electrolytes, so turns on the light bulb well. Okay, you could also have strong acids here. Over here, we have acetic acid. This guy is a weak acid, so he is a weak electrolyte. It's all connected together. Okay, now how can we make this light bulb go bigger? Add more water, because then the water gets pushier and we get a better distribution of those charges. Over here, we show some non-polars. Okay, those guys, they don't split into their ions. There's no chance for helping them out. Non-polar, non-electrolytes. All right, and so now you go, well, where does water fit on the list? Well, water doesn't actually split into its ions unless he has the interaction with other ions. So absolutely pure water is not going to be an electrolyte. But do we ever get absolutely pure water? Any bit of impurities will make your water conductive. Just depends on what the impurity is, how much electricity will cost. So if a weak electrolyte is added to water, then we have weak. If a strong electrolyte is added to water, strong response. If a non-electrolyte is added to the water, then the light bulb still does not go on. Okay. So let's identify which ones here. What was the ones? Strong means a strong acid or an ionic. So do we have any strong acids here? We have HNO2 here. This is nitrous acid. This is nitrous because it's nitrite. So that is a weak acid. So that is not the answer. We have hydrogen gas here. That guy is nonpolar. Why? No lone pairs, because there's no central atom, and they are the same. So their change in their electronegativities is 0. Over here, oh, we have some cation and some anion. So this guy is going to be strong. A strong electrolyte. So he is going to conduct. Nonpolar, nothing. Non-electrolyte. Okay, not going to conduct electricity. And over here, weak, because we have some dissociation. So weak acid still has some dissociation, has some splitting into the ions, but not everything. Some things are keeping in its acid state. So that will light the light bulb weakly. So here we go again. These are the same guys we had before. We already figured out that if they dissolve in water or not. Now we have to decide their electrolyte status. What we saw before, magnesium chloride, we know is an electrolyte. Okay, and he's going to be a strong electrolyte. Why? Because he is ionic. Okay, CH2O. When we drew him, he was polar, but does he have ions? He does not have ions. So he is a non-electrolyte. Carbon dioxide, that's an easy one. He doesn't dissolve in water. We don't even get to look for electrolyte status because there was zero dissociation. 0% dissociation means that there was no splitting into ions. So we can't be an electrolyte because we have no ions to split in. Sulfuric acid, strong electrolyte. Sulfurous acid, weak electrolyte. And now we go over here for conducting electricity. Let's start with magnesium chloride. Strong electrolyte, conducts electricity strongly. Sulfuric acid, strong electrolyte, conducts electricity strongly. CH2O, non-electrolyte, so it can't conduct electricity. There's no electrolytes, no electrons able to create that path for the electricity to leapfrog off of. Sulfuric acid, weak ability to conduct electricity. And last but not least, carbon dioxide. So which one was the easiest one? I saved that one for last. This guy was the easiest one. No, non-polar, non. So that one definitely can be figured out right there. It's not going to conduct electricity. It doesn't dissolve in water, and it's not an electrolyte. It doesn't have ions. So there's no choice. Okay, magnesium chloride is ionic. So that is another easy call there that one has to be left. Figuring out if something's a strong acid or a weak acid, most of the time they are going to tell you on the SOL if it's strong or weak acid. But if you have more oxygens and you're comparing the two, the one with the more oxygens is going to be stronger. That's just the rule of thumb. There's a million rules. You probably will not have to remember all that because it usually will tell you in year one. Okay, and a weak acid, weak. Okay. So lots of different ones here. The hardest one is this guy. Sugar is the same way because sugar is polar, but sugar is a non-electrolyte because he does not change into his ions. He's all non-metals, So he is all sharing bonds. Anytime you see all sharing bonds, non-electrolyte. Sulfuric acid has the H pluses. That's why that guy kind of has a little bit of a weird bonding structure. Strong acid, strong electrolyte. Weak acid, weak electrolyte. All nonmetals and not an acid or a base, non-electrolyte. So lots of little things there. So we talked about these things called colligative properties. Okay, these are simply just properties that do not depend on the specific identity of the solute. So all ionic soluble in water will have this response. All non-electrolytes will have this response. It doesn't matter if it's CH2O or sucrose or glucose. It depends on the concentration. So if the sucrose and glucose have the same concentration, they're going to have the same colligative properties. If the ionic salt has the same concentration, it's going to have the same colligative properties if it has the same ion count. More ions, that's going to give us more of ions in the mix. So that's going to increase its electrolyte status. Okay, so osmosis, water purification. I'm not going to go into this in a lot of details, but this is just one example where colligative properties come into play because it messes with the osmotic pressure that is happening in there. The osmotic pressure is that perfect balance that causes osmosis to stop, which is just moving from a less concentrated solution to a more concentrated solution. Okay. And then reverse osmosis is going the other way, so we can get rid of some of those impurities before you drink the water. Another instance is salt on the roads. We put some of those salts on the roads, and that is going to decrease the freezing point. So we added salt or impurities into the water. It dissolved in the water because it's an ionic and water is polar, and the ionic salts are ionics. And so that's going to decrease the freezing point. So instead of us ending up with black ice everywhere, our freezing point is now moved to lower. So the substance is able to then melt at 0 degrees because we artificially lowered the freezing point by adding impurities. Okay, and so sometimes that seems kind of illogical. So what I want you to remember is impurities slow down the state change process. So if our freezing point is at 0 and we're lowering the temperature, those impurities slow it down. So it can't freeze at 0. It takes longer. So it might take to -4 degrees C or lower for that. And then that also works on slowing down the other direction. If the boiling point of water is 100 degrees, if we have a lot of impurities in it, when we get to the 100-degree mark, we are still working slower than normal. So our actual boiling point is going to be higher. The boiling point is elevated or higher, and the freezing point is depressed or lower. The more impurities, the slower it works. Right, and that's all for today.